In this video, I'm going to be covering the second challenge from the DownUnderCTF 2023 blockchain category called Another Please. So this challenge was marked as an easy challenge, but it is a bit of a step up from the beginner challenge, which we covered in last video. If you haven't seen that, I cover how to set up the environment and connect to the blockchain and to solve that beginner challenge of 8545. If you want to see another please video, that's probably why you clicked on it, stick around. Okay, so let's go ahead and get started. A smart contract is selling Down Under land tickets. Can you get them all? The goal is to own all 30 tickets to Down Under land in your player wallet. So we've gone ahead and I've already gone ahead and deployed this challenge. So we can see we've got all the details here and we've got the contract here. So I'm just going to copy this entire file and put it into our project here, where we have all our solve scripts. So this one is called Another Please. I'm going to paste it in here. So we've got this all here. Now, before I actually start doing the solve script for this, let's go ahead and actually walk through what is happening on this contract. So we can see that there's this kind of big Down Underland thing. We can see it's importing a contract here from OpenZeppelin. So let's go ahead and actually install that. So we can do npm install save dev OpenZeppelin contracts, I think this will work. And while that's going in the background, let's have a look and see what's happening here. So we can see that there's a few constants set, tickets to give away, purchasable tickets. We can see the ticket price is set to a really large amount of ether. And as we can see, if we have a look at our player balance, we can see we only have 1 ether, so that's not a lot. There's a mapping of addresses to bool of free ticket receivers, a counter of how many tickets have been given away, and a couple of errors that are defined here. We can see that this is an ERC721. So if you want to look up what an ERC721 is, that's really important for this. This is basically the non-fungible token standard, or the NFT, where you have a fixed amount of currency where each individual unit of that currency is differentiated from another. So say you have, 1,000 Down Underland tickets, or in this case, there's going to be 30. Each of those 30 is going to be counted as one currency or one token, and they're all distinguishable from each other. So we have a modifier here for ticket not claimed, but let's have a look at these two main functions here. So we have claim free ticket and buy a ticket. So let's go through buy a ticket, because this is probably the one that makes the most sense. So buy a ticket is external and it's payable. This firstly checks if the value of the transaction, so all the currency that has been sent with this transaction, if it's less than the ticket price that's been set, which is that really large amount of ether, it's going to revert and saying not enough funds. If it's greater than or equal to, then it's going to run this gib ticket function, which is this down here, but I'll cover that in a little bit. And then once it has given the ticket, it's going to try and return the change. So if you paid more than the ticket price, then it will return the money back to the sender, and that's what this is doing here by taking away that ticket price minus the message.value and then sending it back to the sender. Okay, cool. That makes sense. Let's have a look at claim free ticket. So claim free ticket is, firstly, it'll run this modifier here, which is ticket not claimed, and it will run if free ticket receivers. So, and remember, this is the mapping between the sender and a Boolean. So basically, if you have received a free ticket, if this particular address has received a free ticket, then we should revert saying the free ticket is already claimed. So essentially, this is enforcing a 1 per address ticket, so 1 ticket per address. So once this is done, then it will do another check down here saying tickets given away. If the amount of tickets that have been given away is greater than or equal to the tickets to give away, which is set to 10 up here, revert free tickets exhausted. So it looks like if you want to claim a free ticket, there's 10 up for grabs and there's 20 that are purchasable. So the goal of this challenge is actually to get all 30 tickets in your player wallet. So then it will run the gib ticket function. Again, I'll cover that in a little bit. And then once the ticket has been given to the sender, it will increase the tickets given away counter and also set the free ticket receivers to true for that particular address so that you can't claim another one. Okay, so this makes sense so far. Now let's actually have a look at this gibTicket function. Now this gibTicket function has an address too, so it looks like it can be given somewhere. It's internal, so this can only be called from within the contract itself. We can't externally access it. The first thing that it checks is if the total supply is greater than or equal than total tickets available. Now total supply isn't a function that's been defined here, but because this contract implements the ERC721 interface, or it is an ERC721 enumerable contract, it inherits from it, this function is available to us to read. So if we want to have a look at the ERC721 spec, we can actually look at ERC721 Open Zeppelin. And these are some really good docs where you can read through this. I think we want to look at the current version. Okay, 4.x and ERC721. And this is kind of gives you an overview of how ERC721 works. And if you want to have a look at the API of which functions you have available to you, you can have a look at the ERC721 enumerable, because that's what this challenge is using. And you can see these are all the functions that are available and events and other things like that. Okay, cool. You don't need to know every single thing, but just that's how total supply is being called here, and it'll be important once we call SafeMint. So yeah, so this is basically checking if the number of tokens that have been minted is greater than or equal to the total tickets available, which is calculated here as just a function as adding the tickets to give away and the purchasable tickets, which is 30, revert as sold out. Otherwise, we're going to SafeMint to a particular address. And this second parameter here is actually given the token ID of what this ID for this particular mint is going to be. And because we're incrementing by 1 each time, the total supply will increment by 1 each time, and that's why total supply will be passed in here as well. So SafeMint, yeah, we'll send it to the address, and that's kind of that, right? Well, this is kind of difficult. So how are we actually meant to solve this challenge? We need to receive all 30 tokens. If we try to claim a token, we can go through, but then if we claim it again, then we're gonna fail because the free ticket's already gonna be claimed. So maybe we could spin up a whole lot of addresses and all of them try and claim it at the same time. Maybe we could spin up a whole lot of smart contracts that do this for us, because the smart contract has its own address. So, but the problem with that is we can only claim 10, and there's 30 tickets that we need in our wallet. And the final problem is if we want to actually buy a ticket, we just don't have enough money. The message.value is always going to be less than the ticket price, because we don't have a way to get our message.value to be greater than this massive number here. So there's got to be something else at play, and there is. And this is actually what is called a reentrancy attack. A reentrancy attack is essentially when the state of the contract isn't updated before an external call is made or some other effect is made. And a lot of people call this the kind of check set effect pattern. This is where you firstly check that all the parameters and checks are in place, like you have enough money, there's enough tickets to be claimed, like all this, like you need to check everything, it makes sense. Then you have effect, which comes directly after that, where you make all the state changes and all the changes that are required before you then have the effect, where you can call or do an external call or do something else. You need to do that check set effect pattern. But in this case, this contract doesn't have that. And where it doesn't have that is in this claim free ticket. So we can see here that it is checking that we have enough tickets to give away. We are checking that the free ticket receivers, like our address hasn't already claimed a free ticket. And then immediately after, it's doing the effect where it's actually going to give the ticket to the user, and then it's doing the set where you update the state variables, where we're increasing the tickets giving away and the free ticket receivers. Now, you may be thinking, well, that's pretty cool, great, but how does that actually help us? Like, this is going to run, and then these are going to run anyway. So what's the point? Why do you need to have it in that order? Well, it's actually to do with how SafeMint function works of an ERC721. Now, if we go to the ERC721 and we look for SafeMint, we can see, this is the definition here. Safely mints this token ID and transfers it to the to address. the token ID must not exist, and if the to address refers to a smart contract, it must implement this ERC721 receiver on ERC721 received, which is called upon a safe transfer. So this is interesting. This is saying that when this token is minted, it must implement this smart contract that is receiving this must implement this interface, which is called upon a safe transfer. So if we click here, if a smart contract is receiving this token, then it has to implement this interface called on ERC721 received, because this will be called to make sure that it's as a safety mechanism for ERC721 that this contract is meant to receive this this token. And for it to be successful, it needs to return the selector of this particular function. So it's a bit confusing, but I think it makes more sense if we do it in code. But the kind of main idea behind this is that this will call our contract that we control before the set part of the pattern of the reentrancy pattern has come into effect. So what this means is, if we go back to the contract, this safe mint function will run. So actually, let's go back to claim free ticket here. So it'll do the checks, and then it will mint us the token. The token will be minted to us. And if we do it to a smart contract, this function will then call that smart contract in that particular function. And all that function needs to do is return that, that specific selector. However, at that point, we can then control the flow of the function calls again, because we own the contract. We can write the code for it. So within that function, we can then, before we return this, re-enter this contract again at claim free ticket. And when we re-enter this, these variables have not been updated. So we're going to re-enter, hence the kind of vulnerability name reentrance, re-enter this contract, re-enter this function, pass these checks again, and then we can get another ticket for free from this contract. And so what will happen is the same thing will happen again. This will call give ticket, which will then call safe mint, which will then call back to our contract again. And then we can do this again and again and again and again, and keep re-entering, because these variables are not actually being updated before the NFT is being minted to the contract. So all we need to do is do that 30 times. And then to make sure that everything passes, at the very bottom, we then just need to return the function selector to satisfy the ERC721 standard. And so once this all pops back out, these will then all be incremented, and these will all be set to true. And we will see that the tickets given away will be actually equal to 30, and the free ticket receivers will be set to true, but it doesn't matter because it looks like we've only claimed one, essentially. So let's go ahead and basically write the contract that's going to implement this. So the first thing I'm going to do is create a new file, and we're going to call it attack another please. Actually, I'm going to call it, yeah, I am. Attack another please, if I can spell. And I'm actually going to copy a lot of this so I don't have to write everything out, and just kind of explain it as I go. So this is the solution. We've got the, same kind of boilerplate stuff. We're importing the another please from this contract here. And the important thing here to see is that this function solve, I'm actually going to rename this to attack another please. This contract here is an ERC721 receiver, which means it implements this interface. And all that means is we need to implement this on ERC721 received. It has these particular parameters and returns a bytes 4. So if we deploy this contract and then we run the solve function, what will happen is we pass in the instance that we want to connect to, which is the challenge instance. It's going to set the owner to the message.sender, and then it's going to call claim free ticket. And claim free ticket is then going to come in here, claim the ticket, check that this contract hasn't claimed anything, and there's no tickets there's enough tickets to give away, and then it's going to safe mint back to this contract. Now, when it runs safe mint, it's going to call this particular function. And from this function, We then increase the called count so we can track how many times how many times this has been called within our contract. We then set up the connection to the another please challenge instance. And then all we need to do is, because we've got the NFT at this point, since this has been called, we're going to transfer that NFT to the player wallet, because this is different from our player wallet because this is the smart contract. The smart contract currently owns it. We want the player wallet to then transfer, we want the player wallet to hold it, so we transfer it to the player wallet. Then all we do is, if the called count is less than the total tickets available, which is just a function that's been given here. So if it's basically less than 30, because we want 30 tickets, then we're going to claim a free ticket. So from here, this then flows all the way back to claim free ticket before this is run, and does the process again, claims the ticket, and then comes back here and keeps going. So now we're slowly transferring all these tickets to our player wallet, because every time this is called, we get a new one and we transfer it to the player wallet. Now, once this hits 30, once this called count hits 30, so we've collected all the tickets, we can't mint another one, because otherwise this will fail, because total tickets available will be 30, and the total supply is going to be 30 as well. So this will fail, saying sold out, and if we revert, the entire state of the blockchain is reverted to before the transaction. So we want to make sure we exit this cleanly. So after 30, we then pop out all the returns. So we're going to pop out bang, 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 all the way out by returning this particular selector for this function. And so this will pop out, finish give ticket. This will then increment and pop out, increment, pop out, increment, pop out, increment, pop out, increment, all the way. And all the NFTs will be in the player wallet. Okay, cool. So we've got our solution. We've got our kind of implementation here. All we need to do is script out how we deploy it and make sure that we can run this. So again, with another please, we're going to copy a whole lot of boilerplate just as helper functions. So let me get these guys, save this, challenge details, and get this. Oh, why isn't RPC URL? Oh, we can fix that while we're here. And the main function, we're calling the main function, is there. And all right, let's start writing out our soul script. So as usual, we can actually copy the first few bits from our previous 8545. So let's copy this. And again, a quick overview of what this does. This will get the challenge details from our API. Now, I'm just going to quickly grab that API, which is here, and put this instead of localhost. And then it's going to create a new provider, which is using this API RPC URL, like the RPC URL we got from the API, to create the challenge provider. So Ethers knows how to interact with the blockchain and where to send its requests to. Then we're going to create a wallet with our private key that we got from the API. And then we're going to connect to the contract. Now, instead of this being 8545, this is actually going to be another please. And the other thing we're going to do is actually compile our contracts just to make sure everything's working okay. Cool. And one thing we need to do is actually update this challenge details to include RPC URL, which is a string, just so we get some typing stuff. Nice. And then let's actually start writing our solution. So we've connected to the contract. We've got our player wallet. We're all good to go. The first thing we need to do is actually deploy our contract. So we're actually going to log this first, basically saying before the exploit, let's see how many tickets are owned by our player wallet. So we're going to go ahead and run that. If we run this now, another please, we should see that we have 0. Cannot read properties, undefined key, private key. Why? Did this last time. There was a little slash at the end. So before the exploit, we can see that the tickets owned by the player wallet is 0. Cool. Okay. So the first thing we're going to do is set up our deployment. So this is a solve factory. So this is basically getting ethers to create a contract factory, which is able to deploy the contract with our player wallet as the private key that does the deployment. Then we're actually going to go ahead and actually deploy this contract from the solve factory. So using solve factory.deploy, make sure it's actually deployed, and then we get our solve contract here. Now, the next thing that we're going to do is we're going to run solve contract. Actually, this is not solve. We rename this to attack another please. Here, yeah, that's all good. Just going to make sure that we have had this compiled so that this is all good. Yeah, it looks fine. Okay, I'm not sure why this is not happy. Oh, there we go. It's better now. So once we've deployed our contract, the only thing that we need to do, again, looking at our contract, is to call this solve function, because this solve function runs the first claims free ticket, which then calls this, starts going through, bang, 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 pops out all that 30 kind of calls deep, and then finishes the solve function. So everything is done through this solve function. So this is a bit of a complicated set of code. I probably could make this a little bit nicer, but essentially we're calling the solve function here, and the solve function, if we remember, has an address for the instance that we're looking at. So we have the challenge instance that we got from the API, which has an address. And so we're passing that in as a parameter, as get address from the challenge contract. And then the second parameter that we're passing in is basically, if there's parameters after the expected parameters in ethers.js, the one after that is basically any transaction options you want to pass in. So the first one here is the gas limit. And the reason I'm setting the gas limit to be higher, or I'm actually setting it in the first place, is because there's a bit of weirdness when there's a whole lot of deep calls, and when you're doing reentrancy attacks like this, for some reason, ethers or the node itself doesn't estimate the amount of gas required for this transaction well, and so it runs out of gas. And this can be a kind of tricky issue to debug. So usually I just set the gas limit to really, really high, because I actually don't care how much gas this uses. I just want it to actually to finish and exploit. So that's why I've set that there. So once this is done, we should actually just check that we have all the tickets, because if it all works well, then we're good to go. So then we have another log saying after exploit, and then we just check the player wallet's balance of these particular NFTs. And then after that, we should have 30, which means we should pass the check, and we could be able to get the flag. So let's go ahead and run this now. If we go npx hard hat run scripts another please. So just to show everyone, before we run this, if we run get flag, the challenge is not complete because we don't own all 30 tickets in our player wallet. Now, if we actually run this, it's taken a little while to do the last bit. Here we go. And there we go. Tickets owned by wallet before the exploit is 0, and after the exploit it is 30. And we can see the flag is there. And if we go back here and run get flag, we can see we get the flag here now. So I hope you understood that. That is the second challenge in the blockchain category of DownUnderCTF 2023. The next video, I'll be covering the third challenge, which is called Monkeying Around, which covers proxies and some delegate calls and some internal storage stuff of the EVM. So yeah, look forward to that, and thanks for watching, and I'll see you around.